Welcome back. So in the last few lectures, we have derived from scratch simple first-order linear differential equations. And today we're going to take a pretty big step going from first-order differential equations where you only have a single derivative dx dt to second-order differential equations where you have second derivatives d squared x dt and things like that. And these systems are going to come up all the time in physics because Newton's second law, F equals ma, is in fact a second-order differential equation. Okay, so I'm just going to start by a simple example, by kind of writing down a simple example from physics where we can write down F equals ma, and then we're going to see how to solve that second-order differential equation. Good. And I think I'm going to solve it four ways. So we'll have four different ways to solve the second-order linear system. So the system I want to look at is called the harmonic oscillator. Harmonic oscillator. And that is just a super fancy term. You've heard harmonic oscillator before probably. It's just a really, really fancy term for anything that oscillates linearly. Like if I have a mass on a spring or if I have a pendulum, those are both examples of harmonic oscillators. These also come up in optics and quantum mechanics, all over the place, electromagnetism. So the example I want to draw is where you basically have, I'm going to draw this horizontally because I don't want to consider gravity. Just imagine that I have a mass m attached to a spring with a spring constant k. Okay, so this is a spring. And we're going to assume that it has a rest position. So there's basically a rest position for this spring k, where basically there's some x rest that's this length, and anything in addition. So the center of mass of this mass from that rest position is going to be called my variable x. So the state of the system that we're going to model, x as a function of t, is basically the position of this mass away from its rest position. So I'm going to do things like I'm going to pull this mass away from its equilibrium and let it go. And you're going to, of course, in your mind see this thing oscillating. X of t is going to give me sines and cosines probably. That's what we're going to model. And we're going to start with Newton's second law. Like I said, we're going to start with Newton's, this is a brand new, very nice pen, Newton's second law of motion, which you all are familiar with as F equals ma, force equals mass times acceleration. And of course, acceleration in this case is the second time derivative of position. So velocity, let's just say, v equals velocity equals dx dt. A equals acceleration equals dv dt, which equals d squared x dt squared. Sorry if that's a little small, but this is what we're all familiar with from basic physics, is that x is my position of this mass away from equilibrium. V is the velocity, a is acceleration. So the velocity is the first derivative of my position in time. The acceleration is my second derivative of my position in time. And this is where that second order is going to come from, is now we're going to have a second derivative in x. We're going to have a differential equation in terms of this second derivative. In fact, this Newton's second law. So how do we derive this? We say, x is the displacement from its rest position, and the force on this mass is proportional to k times x. So this is just, again, this is, I think this is Hooke's law or something like that, where, the more I pull this mass away from its equilibrium, the larger x is, the larger the restorative force from that spring. So the force from the spring force, is, I believe, going to be minus k times x. So if I pull x in the positive direction here, I'm going to have a restoring force trying to pull it back, in the negative x direction, and it's going to be proportional to x. Okay, so this is actually really, really easy. I think the first thing I'm going to do is, we're going to start by assuming mass equals 1 and k equals 1. We'll relax that a little bit later, but we're just, to make my life easier, I'm just going to assume that the mass is 1 and the spring constant's 1. And so what we get when we write down Newton's second law is that d dt of how do I want to write this? So, you can write this as A equals F over m. That's also fine, and m is 1, because I said my mass is equal to 1. So my acceleration is d squared x dt squared, that's A, and that equals my force divided by 1. And my force is minus, k is 1, my constant is 1, I made everything 1. So it's just minus x. That's my differential equation. This is literally Newton's second law. F equals m times a. Okay, force equals mass times acceleration. Mass is 1, my spring constant's 1, so I get x double dot equals minus x. And yeah, if I want to write this in a little bit simpler notation, I'll just say x double dot equals minus x. This is my simplest second order linear differential equation. This comes up all the time in physics. Pretty much any system that oscillates, any system that is periodic and linear, like a pendulum with a small angle, or this mass on a spring, lots of phenomena in optics and electromagnetism and quantum mechanics are also oscillatory and linear, are going to be governed by this second order linear differential equation that we call the harmonic oscillator equation. Okay, so we derived it from first principles. F equals ma is generally speaking going to give us second order systems because A is the second derivative of my position or my state. Good. So now we're going to solve this differential equation 4 ways, and I'm going to build up a bunch of lectures on kind of how to understand these second order systems. Good. I like to start with the easiest approach. So method 1. Method 1. And this is second order systems, literally x double dot equals minus x, in case I erase this. So method 1 is pretty simple. And I actually find this to be a pretty useful approach in differential equations. This is what people have done for centuries, is you guess what the solution is and you plug it in and you see if it works. It's like actually very physical. This is what we call the physics solution. This is what I call the physics solution. Method 1 is guess. Okay, so guess. And what's a pretty good guess for the function x of t? Okay, so we know that if I pull this mass, I guess it's over here, but imagine I'm pulling this mass and I let it go and it starts oscillating. What is a function that oscillates in time? Well, our basic functions that oscillate in time are cosines and sines. Okay, and at t equals 0, sine of t is 0. So if I have a non-zero initial condition, I'm probably going to get something that looks a lot like a cosine function, okay, because it's going to oscillate and it starts off not at 0. So I'm going to assume that my system, x at t, the position of this thing, when at time 0, it's going to have some initial condition. Let's say x at time 0 equals x naught. Okay, it's some non-zero initial condition. And maybe I'll say my derivative, x dot at time 0 equals v naught. Let's say that equals 0. So I start this thing at an initial position, but with no velocity, and then I let it go. That's what this says, is that the initial condition is x naught, and my initial velocity is 0. Then a very reasonable guess would be sines and cosines for this function x of t. And specifically, I'm going to guess that it is a cosine function, because at t0, cosine is non-zero, and at t0, the derivative of cosine is 0. So this matches my initial position 0 velocity. And I'll need to multiply this by x0. Okay? So at time 0, if I plug in 0 for time, x naught equals my initial condition. So this is a very reasonable guess. Okay? And this is what we do a lot in physics and in math and applied math, is you look at your system and you say to yourself, well, okay, this is growing exponentially, or it's decaying, or it's oscillating, and you kind of get some intuition about what you think that solution is going to look like. So of course, x dot of t is going to equal minus sine of t x naught, and then x double dot of t is again going to be minus cosine of t x naught. And you can verify, really simply, almost in your head, that yes, in fact, x double dot is minus x of t. So these functions satisfy this differential equation relationship that has to be true at all times to satisfy Newton's second law, right? Newton's second law is essentially conservation of momentum, and this is true always. It's true for every system that I draw a big enough box around, this is going to be true. And you can verify just by inspection that if I choose this function cosine of t, then its second derivative is minus cosine of t, and it satisfies this relationship. So kind of, in this case, for these linear simple systems, we can kind of guess, and we usually get the right answer. Okay, good. And I'll just write down that, for general mass and k, you're going to get specifically that now, x of t equals, I think, cosine of, sorry, this is so squeaky. Let's see if I can switch to this one. You're going to get cosine of root k over m t times x naught, where essentially this k over m square root is like the natural frequency. So you're basically going to have like omega equals root k over m is going to be the natural frequency of that oscillating mass on a spring, okay? And you can derive this one from scratch. So what you would do is you would not set m and k equal to 1, and you would keep this as minus kx, and you would keep this as m times x double dot, and then you divide both sides, and you get x double dot equals minus k over mx, and you would find, in fact, that this is the solution. So that's a homework for you, is to, again, verify that if I take the second derivative of this, that it equals minus this. Good. Okay, I'm going to erase this, and then we're going to try method 2. Okay, so there's a lot of ways to skin this cat. Don't skin cats. There's a lot of ways to solve this problem. The second method we're going to use is the Taylor series. And again, I don't really recommend, most of the time solving differential equations with Taylor series expansions unless you have to. But I like to show this method because if all else fails, you can always just, expand x of t in powers of t and solve for the coefficients. And it actually is pretty useful at this stage just to build intuition for what's happening. So that's what we're going to do. And this is just like we did in the last few lectures. So I'm going to write down where do I want to do this? I probably don't want to like chop my head off. So let's say I start here, and I'm just going to say, x of t equals some constant c naught plus c1t plus c2t squared plus c3t cubed. And let's say I need to go up to t to the fourth probably, plus c4t to the fourth plus dot, dot, dot. This goes on forever. It's a Taylor series expansion or a power series expansion. So this is only, true if I keep all of the terms in t. And so I'm just going to compute both of its derivatives. So x dot of t is equal to now c1 plus, let's see, I can make this orange, plus 2c2t plus 3c3t squared plus 4c4t cubed plus dot, 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 dot. Maybe I'll write plus 5. I'll try to keep all of the terms because I'm going to be setting them equal to each other. So I'll keep, plus 5 c5 t to the fourth plus dot, dot, dot. And then the second derivative of x dot, x double dot of t is going to, now again, I'm just taking the derivative of x dot of my velocity, and this is going to equal 2c2 plus 3 times 2 c3t plus 4 times 3, remember the power rule, 4 times 3 c4t squared plus 5 times 4 c5t cubed plus dot, 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 dot. And if I had a third order equation with an x triple dot, I'd have to compute x triple dot here, and I would get, more hairy terms. Nothing super complicated. And now I'm literally, just like we've always done, going to set x double dot equal to minus x, and we're going to make sure that the constants at each power of t equal each other, because this has to be true for all time, which means it has to be that the constants equal each other, the coefficients of the t to the 1 power equal each other, the coefficients of the t squared terms, they have to be equal and opposite, actually. They have to equal the opposite of each other, and so on and so forth. So that's going to give me a recursion relationship so that I can write down what is C2 in terms of C0, what is C3 in terms of C1, and so on and so forth. And I think I'm going to use the fact again, because x at time 0 is x0, and if I plug in t0, all of this goes to 0 except for c0. So I probably have the relationship that c0 equals x0. And similarly, if I take my first derivative, x dot at time 0, all of these terms in orange go to 0, and I'm only left with c1. And so c1 is equal to my initial velocity, which we set equal to 0. Okay, so let's say this is equal to 0. Good. You know what? Let's say I had an initial velocity. This will actually be more interesting this way. I hope I don't butcher my notes, but let's say I actually do start with an initial velocity. So I don't just pull this mass and let it go with no velocity. I pull this mass back and I kind of push it a little at some velocity. I give it some little initial velocity, so now it has an initial position and an initial velocity. So in that case, again, x dot at 0, c1 has to be my initial velocity. c1 has to equal v0. And that's enough information now to uniquely determine C2 and C3 and C4 and C5 by equating all of these coefficients in a recursion relation. So let's just do it. So again, remember we're writing x double dot equals minus x. So that means I have 2 C2 equals minus C0 equals minus C0, which implies that C2 equals minus 1/2 x0. That's pretty easy. 2c2 equals minus x0, so c2 equals minus 1/2 x0. Similarly, I get my c3, this term has to equal minus this term, so I get 3 times 2 C3 equals minus C1. And again, C1 is V0. And so this equals C3 equals minus 1 over 3 times 2, which I'm going to write as 3 factorial, times V0. And 2 factorial is equal to 2. Okay, so I've already computed my C3 and my C2 coefficients. So let's see what C4 and C5 are. And I think at that point we'll be able to stop and we'll be able to write down the solution. Maybe I'll switch colors here just to keep it a little neater. So my C4 coefficient is on my t squared here. So I have 4 times 3 C4 equals minus C2. That equals minus C2 because it's this equation equals minus C2, which implies that C4 equals minus C2 divided by 4 divided by 3. And minus C2 is 1 over 2 factorial times x0. And so minus C2 divided by 4 divided by 3 is 1 over 2 times 3 times 4, which is a 4 factorial. Okay, so if that was a little fast, just pause and convince yourself that that's true. I literally take this expression for C2, I minus it, and I divide by 3, and I divide by 4, and that gives me C4 equals 1 over 4 factorial x0. Similarly, for the C5 term here, I have 5 times 4 C5 equals minus C3. Again, that's the t cubed terms have to be equal. And again, that means I'm going to get something that looks like minus, so C5 is minus C3 divided by 4 divided by 5. So that's minus 1 over 5 factorial times V0. And you can go, on and on and on and on forever. Okay, so it's pretty clear what the pattern here is. All of the even terms are multiplied by x0s. All of the odd terms are multiplied by v naughts. And again, if you are pretty familiar with exponential functions and sines and cosines and their power series, you'll recognize pretty quickly that these are starting to look like cosines and sine components. But let's put those all together for x of t and see what we get. Okay, and maybe I'll do it in here. So I have yeah, I'll do this in 2 steps just because I don't want to confuse anyone. So what I'm going to do, the first thing I'm going to do is I'm literally just going to write x of t and plug in all of those coefficients here, and then I'm going to group all of my x naughts and my v naughts. So x of t equals x naught plus v naught t. C2 is minus 1 over 2 factorial x naught times t squared. C3 is, I feel like I'm missing a minus sign. Yeah, this is supposed to be minus. Right, this is C3 equals minus C1, so there's a minus there, and C5 is minus C3, so this is a plus sign. Okay, thank you. I'm sure many of you caught that. So sorry, I already have my C2. Now my C3 term is minus 1 over 3 factorial v naught t cubed, and then I'm going to have plus 1 over 4 factorial x naught again, t to the 4th, plus 1 over 5 factorial v naught t to the 5th, minus dot, 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 dot. Okay, this is literally, I'm just taking this expression here and I'm plugging in what we got from our recursion relationship, from our recurrence relationship for all of these constants, okay, in terms of x naught and v naught. And now I can take all of the terms that are only functions of x naught, and I can take all of my terms that are only functions of v naught, and I can write those down. And I can say that x of t equals, maybe I'll write this in yellow, I get x naught times 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial, minus, I'm sure it's going to be t to the 6 over 6 factorial plus dot, dot, dot. Okay, that's all of my terms that are x naughts. And then I'm also going to get plus v naught times all of these odd powers in t. Okay, so I'm going to get v naught times t minus 1 over 3 factorial t cubed plus 1 over 5 factorial t to the 5th, dot, 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 forever and ever and ever. And lo and behold, this is the Taylor series for cosine, and this is the Taylor series for sine. And so what we find is that x of t equals, need yellow for my cosine. This is cosine of t times x naught times my initial position plus sine of t times my initial velocity. And that is the solution to this differential equation now for a generic initial position and initial velocity. So remember when I guessed, I had to use the simple case where there was 0 initial velocity, or else I might have messed up my guess. When you do the Taylor series, you can actually have your initial position and initial velocity, and it just kind of pops out that you get cosine times the initial position plus sine times the initial velocity. So these are kind of out of phase. So if I start with some initial position and an initial velocity, this is my generic solution. Good. Okay. That was method 2. And this is, again, not recommended to use this every day when you're solving differential equations, but really important to know that almost every solution of every differential equation you'll ever see, you could solve it using these kind of first principles, Taylor series, power series expansions. Good. Okay, method 3. I'm going to erase this and we're going to solve method 3. Okay, we are solving this second order differential equation, which we derived from Newton's second law, F equals ma, for the position of this mass on a spring. So x is the position, x double dot is its acceleration, and the force of the spring is minus x. So this is the differential equation. We've already solved this 2 ways. Now we're going to solve it a 3rd way. So the first time we just guessed cosine solutions because that seemed reasonable given that it's oscillating. It's a springy mass. The second solution was Taylor series. We actually wrote out a Taylor series expansion for x of t. The third method, we're going to guess again. We're going to guess again. But instead of guessing that our solution x of t is some cosine solution, we're going to guess something a little different. So remember, what function, when we take its derivatives, up until a constant looks like itself? So in first order systems, x dot equals lambda x, we saw that the exponential function was the very natural solution, because then if I take the derivative of e to the lambda t, I get something that up to a constant is also e to the lambda t. Just remember, I'll write this out. What function, when taking multiple derivatives, equals itself up to a constant, is similar to itself, has a lot of self-awareness to itself, up to a constant. And so, of course, up to a constant, we know that the answer is the exponential function. I can take the derivative of e to the t as many times as I want, and I get exactly e to the t back. So, x of t equals e to the lambda t is a pretty good guess for the solution of differential equations. Because if I take the second derivative, let's write this down, x dot is going to be lambda e to the lambda t, and x double dot is going to be lambda squared e to the lambda t. So I always get something that looks just like itself, and so I can kind of, again, equate these two equal and opposite to each other. I can plug these two into this equation, and I get that lambda squared e to the lambda t better equal minus e to the lambda t. That's just x double dot equals minus x. And of course, this has to be true for all times, because Newton's second law doesn't ever take any breaks. It never goes to sleep. It never has sick days. It's true for all time that we're aware of. And so this is true for all of these e to the lambda t's, which means that lambda squared has to equal minus 1. That's the only way that this can be true. So lambda squared equals minus 1, which means, I'll switch colors here, that means that lambda equals the square root of minus 1, which is plus or minus I. So lambda could equal plus I or minus I. And this is really interesting. Now what we have is that our solution x of t is going to be written in terms of e to the plus it's and e to the minus it's. Very, very interesting. Because this is a linear differential equation, meaning that the derivative... Okay, that was not a drill, apparently. Those were fire alarms. Okay, because this differential equation is linear, meaning that the derivatives are linearly proportional to the state x, that means that linear superposition holds. So if I have two solutions to this system, then if I add those solutions up, that's also a solution to the system. And so what that means is that the candidate for x of t is now x of t. It could be e to the plus I t, or it could also be e to the minus I t. If I took either of those solutions and I took the second derivative, literally, the second derivative of e to the it is minus e to the it, or I squared e to the it, is a solution of my differential equation, and so is this. So the sum of these two is also a solution of my differential equation. So we're going to say that this is constant 1 plus constant 2. And now we get to determine the coefficients C1 and C2 based on our initial conditions. And specifically, e to the it is going to have a real part and an imaginary part. And so I'm going to also choose C1 and C2 so that it basically is only a real valued function. Because of course, if I pull this mass and let it go, I can't get an imaginary position or an imaginary velocity. I can't get a complex valued position or velocity. And so these coefficients have to perfectly add up so that only the real part of these functions remains. Okay, that's kind of interesting that, I now have these complex lambdas, but of course my position and velocity are still going to be real. So let's do this. And so now I know that e to the it is cosine t plus I sine of t. And so I can write this as, I can basically write down the real part and the imaginary part. I'm going to get something like c1 plus c2 times cosine of t plus I times c1 minus c2 times sine of t. And this is just using Euler's formula, literally that, e to the it equals cosine of t plus I sine of t. So similarly, e to the minus it equals cosine of minus t, but cosine's even, so that's also cosine of t plus I sine of minus t. That's odd, so it's minus I sine of t. And you can plug these in here and get this expression. So now I can use C1 and C2 to essentially give me the initial conditions that I'm looking for, okay? And let's see, is there something? Technically, these constants could be complex valued or real valued. And so I think what I'm going to find is, yeah, okay, let's just work it out. I don't know what the answer is. We're going to try it. So we have some initial condition is that, x at time 0 is going to be just, cosine of 0 is 1, sine of 0 is 0, so that equals c1 plus c2. And similarly, if I take the derivative of this, x dot at 0, the derivative of cosine is minus sine, and sine of 0 is 0, so this term will be 0. And this will be cosine of t, cosine of 0 will be 1. So x dot at 0 is going to equal I times c1 minus c2. And so what that means is that c1 plus c2 has to equal my initial position, and I times c1 minus c2 has to equal my initial velocity. And probably I could figure out using complex analysis that these coefficients have a real and an imaginary part, and I could figure out exactly how to make these add up to equal a real x naught, and their difference times I would equal a real v naught. I'm just going to punt a little and say let's imagine that v naught equals 0. So I just start this thing with an initial position and let it go. Then that means that c1 has to equal c2. Okay, for this to equal 0. And that means that C1 equals C2. So C1 equals C2 equals x naught over 2. You could definitely solve this for a non-zero velocity. I just don't want to do it on the spot right now. That might be a good homework problem, is kind of work out the complex analysis if this is a non-zero v naught. But for initial velocity equal to 0, these constants have to equal each other, and they both equal x naught over 2. And so that literally means that the solution again is equal to x naught cosine t. Good. Okay, so that again is a third way of confirming our intuition that this thing is going to be built up of sines and cosines, and that these constants are going to be used to get my initial condition and initial velocity. Okay, I'll erase this and show up the fourth method, and we'll just briefly talk through that. Okay, so the fourth method, I'm just going to write this down. I'm actually not going to solve it using this method, but this is going to be the basis of a lot of the future lectures. Is method 4 is what we're going to do is we're going to introduce a new variable. This is called suspending the variables. So suspend variables. Essentially what that means is that we introduce a new variable v. Introduce a new variable v equals dx dt. And I'm going to turn this second order linear differential equation into a system of first order differential equations. So I'm going to say x dot equals v, And now v dot equals minus x. And this allows me to write this as a matrix system of differential equations. So now I can have a vector x and v, and ddt of this vector is going to be a matrix times that state x and v. So ddt of x is v, so that's 0, 1. That gives me x dot equals v. ddt of v is minus x, so I put a minus 1 here and 0 there. That is that equation. And now I went from a second order system, meaning I have second derivatives, because Newton's second law has second derivatives. Now I have a system of two first order systems. These are only first derivatives. So this is a system, kind of a matrix system of first order ODEs. And you can always do this. If you have a second order system, you can get as a system of two coupled first order equations. They're coupled because x dot depends on v and v dot depends on x. If I have a third derivative in x triple dot equals something, I could write this as a system of three variables and so on and so forth. So I'll show you all of this in the next lecture. But what's really neat here is that this vector now is the state of my system that uniquely defines my system, the position and the velocity. And now I have, an initial condition that again is a vector, x naught, v naught. And I'm going to show you in future lectures, when you write this system ddt of, let's call it x and v, equals this big A matrix. This is a 2 by 2 matrix now, times x and v. And I'm going to define this state x and v. We're going to call this like the bold. This underbar means it's a vector state. Okay, that means the state with two components. We're going to see that x dot equals matrix A times x has a solution, which is x of t equals the matrix exponential e to the a t times my vector of initial conditions x at time 0. So I'm going to show you all of this in the future lectures. This is how we solve really big systems of equations or really high order systems, is by writing them in this matrix system of equations way. And teaser, those lambdas that I showed you, those lambdas that equal plus and minus I, those are the eigenvalues of this A matrix. Okay, so the eigenvalues of this A matrix, when you suspend variables and write this as a system of first order equations, the eigenvalues of that A matrix are the lambdas, the kind of e to the lambdas that you would use to solve the system. So that's going to be a deep connection. That's how we're actually going to derive the eigenvalue and eigenvector equation, is to solve these equations, and that's all coming up soon. Thank you.